Welcome back to this course on blockchain and its applications. So, in the last class we have seen this crash fault tolerant algorithm in the context of Paxos, and we have discussed about the safety and the liveness property of Paxos. So, today we are going to talk about another class of consensus algorithms when the fault is more severe than crash. That means the nodes start behaving maliciously, and that class of faults we call as the Byzantine fault. So, we are going to see that how we can reach consensus in the presence of a Byzantine fault, and from there we are first going to look into the notions or the properties of an Byzantine agreement system, and then in subsequent lectures we will move towards developing consensus mechanism to support or to tolerate Byzantine faults. So, let us start our discussion on Byzantine faults. So, in this lecture we are going to cover about Byzantine faults and the properties of a Byzantine faulty system, or rather going to look into how a Byzantine faulty environment work, and then we are going to look into one important notion of Byzantine agreement protocol, certain limit on the number of nodes in the case of Byzantine agreement protocols in an asynchronous environment. So, these are the keyword for today: BFT consensus and BFT agreement. Now, one important thing that I would like to mention here, that although typically we try to or many a times we basically interchangeably use these terms consensus and agreement, these are kind of two different notions. So, the agreement basically means a kind of temporary state on consensus. So, it might happen that you can run the agreement protocols multiple different times to reach consensus, and that way there is a kind of minor difference or a slight difference between this agreement protocol and the consensus protocol. So, for example in the context of Paxos, we had seen that it works on two rounds. In the first round it comes to an agreement in terms of the round ID, and in the second round it tries to propose an value and come to an agreement on that value. So, there are two agreement protocols which are running there in that particular consensus. So, these things will become much more clear in the context of BFT consensus, which we are going to talk today, starting from this lecture, and you will learn that how this Byzantine fault can be tolerated in a distributed environment, and this is something which is very much important for us for designing the consensus algorithms for a permissioned or a closed blockchain network, right. So, these Byzantine fault tolerant algorithms are widely used in closed blockchain network. We are going to have an hands on with Hyperledger Fabric, and you will see that in Fabric consensus we use one Byzantine fault tolerant algorithm called PBFT. So, that also we are going to look into in the next lecture and subsequent lectures. So, to start with, in the last lecture we discussed about this problem with Paxos. We had seen that Paxos can tolerate crash fault, but we asked this question that what happens that one of the acceptors in Paxos starts behaving maliciously. So, now let us try to see that what happens in that context. So, what is the corresponding malicious behavior that we had noted? So, the malicious behavior was for acceptor 2. Now, in case of acceptor 2, ideally when acceptor 2 has already sent and promised message, so when it was receiving a prepare message from proposer 2, ideally it should have ignored this message. But rather than ignoring this message, what acceptor 2 has done, it has sent another promise message against 50. Well, now let us see that what blunder this acceptor 2 has done by sending this promise 50, by violating the basic principle of Paxos and trying to deceive the network from the normal behavior to some kind of malicious behavior. So, this is one type of malicious behavior that can be done by an attacker, right. Rather than sending the intended message, what you do that you send a different message through which you try to deceive the network from its regular behavior or from its normal behavior. So, such kind of things are happening here. So, when this happens, so in that case this acceptor 3 it receives this prepare 50 first. So, acceptor 3 sends back a promise 50. Now, at this stage what we see that proposer 2 has received the majority with 50 and proposer 1 has also received the majority with 50, because I have 3 nodes here. So, if I have 3 nodes, then or 3 nodes or 3 acceptors, then my majority is 2. Well, so that means the moment you are going to receive 2 messages, you will believe that you have received the voting, received the messages from the majority, and you can agree on, you can think of that the majority has agreed on this stage. So, as a consequently, proposer 1 sees that it has received 2 promise messages with ID 100. So, proposer 1 believes that well it has received the majority. Similarly, for proposer 2, it also have received a message with 2 different 50s. Well, so proposer 2 can also believe that it has received the majority. Now, in this way, what might happen further, that they can change the accept message. So, this AR means accept request. Just to put it in this space, I have shortened this notion. So, it sends the accept request message, because here both proposer 1 and proposer 2, they sees that they have received the promise messages from majority of the acceptors. So, because they have received the promise message from majority of the acceptors, they can believe that well now they are, both of them are eligible to send the accept request message, and that thing happens here. So, both have send the accept request message, but with different values. So, one have proposed for a dinner, another one has proposed for a movie. Well, now the same thing can get repeated here as well by acceptor 2, because acceptor 2 is a malicious node that is trying to do something malicious here. So, it will send the wrong message, or it will keep on sending the wrong messages. So, that way acceptor 2, what it does, although it should have ignored accept request with ID 50, but it does not ignore that, it sends a accept message to that as well. So, it sends an accept message to proposer 1 with ID 100 and value as dinner, and at the same time it sends another accept message with ID 50 and value movie to proposer 2. Well, now at this stage proposer 1 believes that they agreed for the dinner, and proposer 2 believes that they agreed for the movie. Well, and this is something which is dangerous here. Well, because here you see that 2 different proposers, they have agreed on 2 different stuffs. Well, and when 2 different proposers have agreed on 2 different stuffs, in that context you cannot say that they are still in a safe consensus. So, the safety property gets violated. So, that way what we see, that when you have such kind of faulty nodes in your system, and that faulty nodes behave something like what we call as the malicious behavior. So, it violates the regular protocol and it starts to send message which it is not supposed to send. So, it was supposed to ignore the message, but rather than ignoring it, it keeps on sending the replies, and that can create problem in case of Paxos. So, that way Paxos cannot tolerate such kind of fault. Now, such kind of fault has a name that we used earlier as well. We called it as a Byzantine fault, and this idea of Byzantine fault it emerged from this particular problem which is known as the Byzantine general problem. Now, this is an interesting problem that was first proposed by Leslie Lamport in a pioneering paper that talked about this kind of consensus mechanism, and in that paper they tried to discuss that what is this Byzantine general problem, and how you can possibly solve Byzantine general problem in an synchronous environment, not in an asynchronous environment, because solving Byzantine general problem in an asynchronous environment is much harder compared to solving it in an synchronous environment. So, let us look into Byzantine general problem in detail. So, the Byzantine general problem is something like that. Say you have a fort and you have a set of commanders or a set of generals who are going to collectively attack to this fort. So, assume that this fort has 2 different doors, and 2 different generals are going to attack both the doors simultaneously. Now, when they attack both the doors simultaneously, then they can possibly win the battle and can conquer the fort. but otherwise if they attack on different time, if they cannot or if they fail to attack simultaneously on both the doors, then they might fail the battle. So, what they do, they wait for the instruction from the commander, and when the commander says to both of them that hey, attack on the corresponding doors, they collectively do the attack. Well, now what happens here, say when the commander sends this attack message to both the lieutenants can attack simultaneously and they can actually win the battle. Well, so that is the kind of normal scenario and the general scenario where all the people are happy. But then what might possibly happen in this case, that this commander might be a kind of faulty commander or a malicious commander, and what the commander might do, that the commander might say attack to one of the lieutenants and retreat to another lieutenant, and say the commander has taken the bribe from the king of that fort, and the commander is doing in this way, ensuring that well only one of the lieutenant attack at a point of time, and that way they are going to lose the battle. Well, so that way such kind of faulty instructions may prove severe, and what we would need here, we need to design a mechanism to reach a consensus. Well, so the lieutenants, rather than just getting the command from the commander, they will not immediately obey it, but what they will assume that the commander might be faulty, the commander might have taken bribe from the king of that fort, and that way they will try to reach to a consensus. And earlier we had seen that well we can possibly reach consensus with this majority voting. Well, so let us try to see here whether majority voting still works for reaching consensus in this particular problem or not. So, how this voting works? So, these two lieutenants, what they do? They try to share that information among themselves. So, whatever they had received from the commander, they inform it to the other fellow. So, lieutenant 1, it had received an instruction of attacking the fort, so it forwards that information to lieutenant 2. Similarly, lieutenant 2, whatever information it had received from the commander, it sends back to that information to lieutenant 1. So, here lieutenant 2, it has received a retreat from the commander, and that is why it sends a retreat message to lieutenant 1. Now, the question comes that by sharing this message, can we reach consensus? So, this is an interesting problem. Why that is so? That lieutenant 1 might be able to see that well it is receiving different messages. Well, it sees that well commander 1 has sent attack and lieutenant 2 has sent me retreat. So, there is something fishy or something problematic here possibly. Similarly, lieutenant 2 can also find it out. Well, so lieutenant 2 sees that well my fellow lieutenant has told me to do the attack, but the commander has told me to retreat. Well, so there is something fishy or there is possibly something problematic. But the question is that what is the problematic behavior? Well, so in this context I would try to mention something here which is important. So, there are two notions of Byzantine fault. Well, whenever you are going to treat with such kind of fault. One notion that we call as the Byzantine fault detection, and the second notion is the Byzantine fault tolerance. Now, these two notions are actually different. Why they are different? Because in case of Byzantine fault detections, or what we call it as BFD in short form, I need to just find out whether certain Byzantine behavior has happened in the environment or not. Well, just assuming that I myself is not the Byzantine node, but I am trying to find out whether certain kind of Byzantine behavior has already been observed on the system or not. Now, here in this particular scenario, what you can see that well possibly the lieutenant 1 and lieutenant 2 can detect that certain Byzantine behavior has happened, because if there is no Byzantine behavior, then both of them could have received the same message. Both of them will either receive attack or both of them will receive retreat. But the problem here is that one has received an attack and another has received an retreat. Well, so that means certain problem has happened in the system, and that is possibly a Byzantine fault. So that way, with this particular system, by sharing the message between these two lieutenants, you can detect the Byzantine fault. But the question comes that can we tolerate the Byzantine fault? And whenever I am saying that to tolerate the Byzantine fault, that means I would like to reach consensus even in the presence of Byzantine fault. Now, this consensus or tolerating Byzantine fault has a different notion. What is that? It is not only that I am going to detect that there is an Byzantine attack, rather I am also going to infer the current agreement in the presence of Byzantine attack. Well, so the fault detection only talks about detecting a Byzantine attack, which is possible here. But the moment I am saying that I need to make the system BFT, that means Byzantine fault tolerance, so I would like to reach to a consensus. At that moment, it is not only that I would detect that something fishy has happened or some Byzantine attack has happened, but I am also going to come out of that Byzantine attack. I will try to see that whether I can infer that what is the actual message that I should follow, well, or at least whether I would be able to detect that who is the faulty person here. Now, this is important to find out with BFT consensus, that it is not only about whether there is a fault, but it is also about who is faulty. Now, here you see that in this particular scenario, although we are able to detect that there is a fault, but we cannot say that who is faulty. Why that is so? That is because it might also be the case that the commander is a good commander. The commander sends attack to both the lieutenants, but now one of these lieutenant is faulty. Now, when this lieutenant is faulty, what the lieutenant is going to do? The lieutenant is going to send the wrong information. So, although this lieutenant has received an attack from the commander, but the lieutenant is going to say that, hey, I have received retreat from the commander. Well, so here you see that in this case your problem is that although you are able to detect that certain Byzantine fault has happened, but you will not be able to say that who is Byzantine, whether the commander is Byzantine or whether one of the lieutenant is Byzantine who is going to relay the message from the commander. Well, so it might also be the case that the commander is doing the correct thing, but one of the lieutenant is faulty and one of the lieutenant is behaving maliciously. Well, so this is something we also need to address whenever we are going to generate or going to discuss about a Byzantine fault tolerant system. Now, what we have seen here that consensus is impossible with one commander and two lieutenants when one is faulty. So, we cannot make the system Byzantine fault tolerant, although we can detect a Byzantine fault in this case. So, let us try to see a different scenario and try to see whether we can detect a Byzantine fault and at the same time whether we can tolerate a Byzantine fault in that context. So, what we are doing here, that here I am just increasing the number of lieutenants. So, rather than a single lieutenant, now I have 3 lieutenant and 1 commander. Well, and let us try to reiterate the same thing. So, what I am doing, that assuming first that the commander is faulty. Now, when the commander is faulty, what the commander is going to do? The commander is going to send attack to 2 of the lieutenant and retreat to 1 lieutenant. Now, when that is the case and I say that the lieutenants are also going to share the messages among themselves. So, that same thing happened, the lieutenant who has received a retreat, that lieutenant sends a retreat to others, and similarly the guys who have received the attack, they forward that information to others. Well, now at this stage with every lieutenant, let us try to see that how many attack we have received and how many retreat we have received. Now, what we see that for all the 3 lieutenants, you have received 2 attack and 1 retreat. Well, so for example, for this particular guy, it has received an attack from the commander, it has received an attack from this particular lieutenant, but it has received a retreat from this guy. Well, similarly for the second lieutenant, that is for this guy, it has received a retreat from this one, it has received an attack from the commander, it has also received an attack from this first lieutenant. So, you have 2 attack and 1 retreat. Similarly, but for the third one, for which the commander was faulty, commander sends a different message called retreat. So, what we see that, well, it has received a retreat from the commander, but it has received attack from both of its fellow lieutenants. So, it receives 2 attack and 1 retreat. Now, in all the 3 cases that we see here, that is 1, 2 and 3, in all the 3 cases we see that the majority is on attack. Well, so that means what we can say that, well, at consensus we are going to agree on attack, because that is something that have been voted by the majority. Now, you might ask me the question that what happens that rather than sending attack to 2 of the people and retreat to 1, what if the attacker sends, say, make this attack as a retreat. So, it sends retreat to 2 of the friends and attack to another fellow. Now, if that is the case, then also we are going to reach to consensus, but at that time we are going to reach consensus on the value retreat. Well, so that means it is not important for us to reach to consensus on a target value. We can get any of the value at the consensus, but what we try to ensure that whatever be the value, on that value all the commanders who are there, they collectively agree on that. Well, so this is particularly the Byzantine general problem that we have, and in this Byzantine general problem what we see that, well, we can reach consensus when the commander is faulty. Now, at the same way, let us try to see that whether we can also reach to consensus when one of the lieutenant is faulty. Now, here say the commander is a good commander, the commander sends attack to all the fellow lieutenants, but one of the lieutenant is faulty. So, the faulty lieutenant is going to send attack to one of its fellow lieutenant and have sent a retreat to another of its fellow lieutenant. And that way whatever have been received from the commander, the other fellows also relay the same. So, they have received an attack, so they only relay the attack. Now, in this case, if I try to calculate number of attack and number of retreat, we will see that for this particular lieutenant I had 2 attack, 1 retreat. For this one I have 3 attack, 0 retreat. For this one also I have 3 attack and 0 retreat. Now, in this case what we see that although the commander is faulty or a lieutenant is basically faulty, but even in the presence of lieutenant a faulty lieutenant, all the lieutenants they agree on the same value, that is an attack that have been voted by the majority. Well, so that way what we particularly see which is interesting in this context, that when I have 1 commander and 2 lieutenant, I can detect a Byzantine fault, but I cannot tolerate it, I cannot reach to a consensus. But whenever I have 1 commander and 3 lieutenants, in that case, irrespective of whether the commander is faulty or one of the lieutenant is faulty, we can always reach to a consensus. Well, and whenever we have been able to reach to a consensus in the presence of BFT, you can also say that, well, we have also detected, we can detect congestion in that case. Well, we can detect that certain kind of Byzantine behavior has happened in the scenario. So, in this case also, as we see that we can reach to consensus. So, in case of Byzantine agreement in an asynchronous network, we have one important postulate that can get directly derived from the example that we have seen, that if you assume that you have f faulty nodes, you need at least 3f plus 1 number of nodes to reach consensus. Well, now that way when you have one faulty node, in that case your total number of nodes should be 3f plus 1, that is equal to 4, and that is the reason with one commander and two lieutenants, well, that means a total of 3, we are not been able to reach consensus, well, although we can detect the Byzantine fault. But in case when we had one commander and 3 lieutenant, in this case I have a total of 4 nodes which is satisfying this bound, and we can see that we can reach consensus. Okay. Now, the question comes that how you are going to have a proof of this particular theorem. Well, we have seen an example. Now, to have a proof, we rely on this factor that this kind of Byzantine nodes, they create partition in the network. Well, so what is mean by partition? Partition basically means that this particular node are going to send one message to one part of the network and another message to another part of the network. Well, so let us try to have a kind of visual proof or a conceptual proof for this particular theorem. So, there are many different formal proofs which are there in the literature. You can look into the paper, you can look into the original paper by Lamport to get a formal proof, but here I am trying to explain the proof in a easy way and in a kind of more conceptual way. So, assume that you have a total of 3f number of participants, well, and in this 3f number of participants I am assuming that f number of participants are faulty and they are Byzantine faulty. Now, when they are Byzantine faulty, I am assuming that these middle nodes are Byzantine faulty, that means these nodes which are under this red set, they are the faulty nodes, and the nodes which are in the green set, they are the correct node. Now, here this faulty node, what they have done, they have created a partitioning in the network. Well, so there are f number of nodes in its left and there are f number of nodes in its right. Now, in this particular case, what might happen? I just name these 3 partition as partition left or PL, partition faulty or PF, and partition right or PR. And what these faulty nodes are going to do? These faulty nodes, I have said that these are Byzantine nodes and they are going to create partition in the network. Partition in the network means send different information to different part of the network. So, that is the thing that they do. So, for example, they send 0 to one part of the network and 1 to another part of the network. Now, in this case what you see that this PL and PR cannot communicate with each other, well, because they are sending the message via PF and PF have created a partition in the network. Now, when that is the scenario, then what I have to do, either PL need to break this tie, well, or PR need to break this tie. So, currently they cannot break the tie, because if I am considering PL and PF, then I have f number of nodes in both the side, f correct node, f faulty node, I do not have any clear majority. Similarly, if I am considering PF and PR together, that they are going to help in reaching to the consensus. There also I have equal number of nodes in both the partition. So, I have f number of faulty nodes as well as f number of correct nodes. So, that way none of the PL or PR will come to an agreement. So, what we can do here, we can just put up one additional node either in PL or in PR to break this tie. So, let us put up an additional node at PL, and this particular additional node which I have put up here, this additional node is actually helping me to break this tie. Well, so this node is ensuring that, well, in between PL and PF, PL is the majority. So, that way what PL is going to tell, that is going to get accepted in the consensus. Well, so that way I see here that I need a total of 3f plus 1 node. So, that even if you have partition exactly at the middle, then also you can reach to consensus. Well, and you may ask me the question that what if I am not making the partition at the middle, rather I am making partitioning at the right. So, if you are making partitioning at the right, so if you are just assuming that well this set of nodes are the faulty node and these nodes are the correct nodes, then easily you can reach consensus, right, because you have 2f number of nodes here and a plus 1 nodes here. So, putting the faulty nodes at the middle has the most impactful scenario when it exactly it creates a partition of half in both the side, and that way no one would be able to communicate with each other to reach consensus. So, this particular postulate that if you have f number of faulty nodes, then you need 3f plus 1 nodes to reach consensus, that is very important for our context, and you should always keep in mind while designing a BFT consensus algorithm. So, in conclusion, today we have seen that Paxos does not work with Byzantine fault. So, Paxos is much harder to solve, that Byzantine faults are much harder to solve compared to crash fault, and when we have f number of faulty nodes, we need 3f plus 1 nodes to reach consensus in an asynchronous BFT system. So, with that I would conclude today's lecture. In the next lecture, we are going to learn about the BFT consensus protocol. So, just like Paxos, we are going to see one of the most popular BFT consensus, which is called PBFT or practical Byzantine fault tolerant. So, in the next lecture, we are going to look into PBFT in details. So, that is all for today. Thank you all for attending. See you in the next lecture.